Hello everyone, and welcome to another new video. So I have no idea how long this video is going to be in the end, but it is, well, on my side it's going to be a rather substantial project. So here we have an unmodified GTX 580 reference card. It is technically made by Point of View Graphics, even though they're OEM. It's obviously EVGA in this case, as you can see here. They've been using a couple different OEMs, like I have another card of them that's just green. But yeah, so the components on the PCB are the same as on the reference PCB. And the thing I wanted to do with this one is sort of quantify and test what actual impact the modifications that I and other extreme overclockers that actually have. So yeah, so what you can achieve by cap modding things, volt modding things, that's pretty much it actually. Those are the two mods that you would do. Cap mod would be a bit more interesting because there's like, you can cap mod memory, you can cap mod core, and using different types of capacitors. So yeah, and then in terms of volt mod, well, it's a simple feedback mod for both of these controllers here. And that would be it. And yeah, so what I thought I'm gonna do here is record the baseline from the card, just as it is here. Reference heatsink, reference PCB, reference... Well, actually this one comes with a BIOS that has the fan unlocked to 100%. The other reference cards I had it locked at 85%. But, well, I guess you could also just, like... I'm just gonna have it at 100% then. Like, you could always have just a slightly colder ambient and then it would have like the same effect. So yeah, I'm gonna record a baseline of what the card can do. And then I'm gonna start doing mods with increasingly more like craziness. So I would start unlocking the BIOS. Then I would put capacitors on the card. Then I would put some other capacitors on the card, and then finally I would Voltmod the card, and then, well, you can, since this is a Fermi card, you can also delete the core. Sadly, that will force us to use a different heatsink, which, well, I guess in the end I could just throw this on water cooling, since now my new radiator has arrived and I have the new loop finished. So yeah, basically this is just gonna be standard reference card. Yeah, I'm gonna record a baseline, so binning isn't that big of a deal. I'm going to show my binning chart again. Since every Fermi card I get, I bin at 2 sets of voltages and record temperatures and all that stuff, so you can compare how good cards are. I've already binned this one. This is it's a decent one. It's a decent card. The memory on it sucks though. But yeah. One last thing you should keep in mind, this is a GTX 580. If we are going to do some mods here, especially I pretty much already know that the memory will probably not change a lot because it is running 1 gigabit Hynix AFR. You could have an identical card to this one, but you could have different memory chips. You could get a Samsung 1 gigabit eDie, for example. In my experience, the eDie memory chips are much better for scaling than the Hynix AFR memory chips that we have on here. So, just like Silicon Lottery, just like binning, every card will respond a bit differently based on what exact components you have, how good those components are, like ASIC quality is a factor here. And also, this is a GTX 580. If you have a different card, even if it's a 480, which is technically the same architecture, they do behave differently. So, yeah. But as a sort of general display of what the mods actually do, it should be enough. It's just like you can't apply this, like the exact values you get here to like a 1080 Ti or like a 6900 XT. That just doesn't work. It's different cards, different architectures, and different generations. But yeah, let's not ramble too much and get right into it, showing you the binning chart and the baseline of the card. So here we are. I had to print out the binning chart because apparently recording my desktop was too difficult for NVIDIA and it trashed 2 recordings. So yeah, we're doing it like this. So here we have the binning chart. You've seen this before, it has grown since. And our card in question is this one. So this column, or like, is column the right word? I don't know. So, I guess I should say how this works. So we have 2 tests for the core. We have normal VCore and we have overvolt VCore. The reason why I do this is because if you look at the results, you will see that some cards gain less extra clock speed from raising the voltage, and that's basically why I do this. That's what I want to see, if the card has huge gains or smaller gains from going to higher voltage. Then we also have, like, I only run the memory voltage stock. So yeah, we only have 1 test for that, just maximum memory frequency. Then we have what memory IC we have, and density. All of this is 1 gigabit, so just says 1G. And as I've said, our card has Hynix AFR 1 gigabit, which, well, if you look at this, AFR is not that great. Our card actually has some pretty good AFR, but like the other AFR cards, like, yeah, these are pretty much the worst. The best performing stock is a Samsung G-Die. As you can see, it reaches 2400 megahertz. E-Die is also pretty good, just not on this chart, because E-Die just takes more voltage and cold, like it scales with temperature. If you take it colder, it goes faster, and if you give it more voltage, it goes faster. Neither of that is it is receiving here, because stock heat sinks, stock voltage, so the E-Die is not performing that great. But yeah, like E-Die has scaling where AFR does not, because like I've modified AFR cards before and they've actually gotten worse for more voltage. I'm still going to do the mods here to show you how it works. It's just we will probably not see that much improvement here because, well, we have AFR. But if you have a card that has like E-Die, yeah, your memory is gonna get a lot faster if you mod it. Then we also have temperature, just to give us an idea if maybe the clock is being limited by temperature, just like here. The Jet 580 direct CO2, it has a very not good stock heatsink, so the overvolt clock is very low. Even the stock clock is kind of low. Like, it has a good core. You can see the AC quality here, except for this card. I got pretty lucky with AC quality, so good AC quality doesn't always mean you will get a good overclock, but it is generally a good measurement of how well the card will clock. There are some outliers though, like you can have really high AC quality and bad clocks, and the reverse also. Like this 480 here, for example, that's a pretty high clock on a very low AC quality. Yeah. But our card, well, we are better than 70% of GTX 580s. I guess that's a good amount. And in terms of actual clocks, we got 860 megahertz at the normal VCore level, which is pretty much stock voltage. Yeah, like considering that like all of these cards are pretty, except for that one, pretty much all of these have pretty high AC quality, and especially the Lightnings, just their cores are really clocking really high. So yeah. But as far as clocks go, I think our 580 here is actually pretty good. So 860 stock voltage and then 966 with overvolt. That's a pretty good result. It doesn't really like it looks about average or slightly below average if you just look at this list. But yeah, like I think I just got pretty lucky with my cards, because I've seen plenty cards on the internet that can't even do 900, and you can see like every single card here did 900 megahertz. There's a lot of cards out there that can't, from what I've seen. So the card is pretty decent, I would say. Like, it's pretty decent already. Yeah, so I hope that at least the core. I don't think our memory will really change with mods, just because I've had AFR in the past and it actively just got worse with more voltage, and Capmods didn't do anything. But I am hoping that the core will do pretty good, because 966, that's a decent result. Also, this card got a bit hotter than the other ones. So if we just keep the card colder, it might actually get like 975 like these ones. For example, like this one at 58, this one was 69. And also this was 66. Like, this is, even though all these cards, like, well, actually, this one has a custom one. This has the reference cooler, this has the reference cooler, this has the reference cooler, this also has the reference cooler. The differences in temperature, actually, yeah, I don't think my ambient temp fluctuates that much, because I pretty much always keep the room pretty cool. But yeah, maybe it was just kind of a hot day. Like, this temperature is pretty high. And I think I said, like, in the end, we will probably throw the card under water cooling, and then that issue will be gone. So, as far as the baseline goes, the core's pretty decent. The memory, for AFR, it's performing good, but it is still AFR. So the memory will probably not really go that fast. But the core looks promising. So yeah, I guess that's the baseline done, and we can now get into modding the card, which the first step, which I would say the easiest step, is modding the BIOS. So you don't need a soldering iron for that, you just need a program called Fermi BIOS Editor, and then you can edit your BIOS. Specifically, we will unlock the voltage limit to go beyond this 1.15 volt limit. And, well, our card already has an unlocked fan, but I've had reference cards that only can go up to 85% fan speed. This one can already go to 100 from the factory, but if you have one that can't, you can also unlock the fan speed by doing that. So let's do that now. So now we are on the desktop, ready to do our BIOS modifications. Now, to extract the BIOS, we need GPU-Z, and you just press this button, say save to file. I've already done that, so this is our BIOS right here. And then you would get your Fermi BIOS editor. Open BIOS, you select the BIOS, and you see it says unsupported device. So some GTX 580 cards, including this one, are not able, like, the BIOS of them can't be read by Fermi BIOS editor. That's a limitation I wasn't able to work around, so we cannot modify the BIOS on this card. We could download a BIOS from, say, Tech PowerUp that is readable and could change that one. I'm not going to bother with this here, because we would only get extra voltage range, and we're going to get that anyway with our Voltmod in the end. So it's not really a big roadblock. It's just like, if you didn't want to Voltmod your card, you could maybe get more voltage this way. On this card, sadly, it doesn't work. So yeah. One disclaimer for downloading BIOSes from Tech PowerUp, though. On Tech PowerUp, it only tells you what manufacturer of memory chips the BIOS is compatible with. It doesn't say which revision. Now, that's an issue, because different revisions of, say, Hynix, Samsung, or Elpida or Micro memory chips have different timings. And if those timings mismatch because you flash a BIOS for one revision and you actually have another, that will lead to artifacting and maybe not even booting. You would then, well, if the card doesn't boot, you will need an EEPROM reader writer. If it does boot and does artifact, you can just flash it again. So yeah, be careful. That can happen. Usually when it happened to me, I always was able to boot back up and reflash the card. I haven't bricked the card yet, but it is theoretically a danger that can happen. So yeah, sadly we cannot modify the BIOS of this card. if there's a fix for this to make this work, I'd be happy if you tell me in the comments. I do not know of any way to fix this. Some of the reference cards, and it's only reference cards in my experience, just have this unsupported device thing, and you cannot change their GPU BIOS. So yeah, that's that's basically this part done. Pretty anticlimactic. Well, it didn't really do anything because the BIOS seems to be encrypted or unreadable or having a different device ID that's not recognized by Fermi BIOS editor. We would have just used NVFlash. You can see I have a lot of just random BIOSes in here. We would have just used NVFlash. You can look up a tutorial for that, how to use it. It's not that hard. It just involves some CMD command line stuff, and then you can flash. Do it in safe mode. This is not safe mode. Better reboot in safe mode and do that. But yeah. So sadly there's no modifying the BIOS on the card. Which, well, it is kinda unfortunate that I won't be able to show it to you in this video. But, well, you can look up a tutorial for NVFlash, and anyway, the only thing we would have done here anyway is just extend the voltage limit, so we can, if we go into MSI Afterburner, you would be able to put in more than 1.15 volts. As you can see, and probably here, the fan is already unlocked on the card to 100%. Other reference cards I had were stuck at 85. And the fan really doesn't want to calm down now, so I guess this is a good time to get to the next part. So, since our BIOS editing attempt didn't really work out, we just go to the next step, which would be attempting a cap mod, a capacitor mod on the card. Now, if I can gather some of my capacitors over here, examples are these. I have some 1000 microfarad and some 820 microfarad capacitors that I'm going to add to the card. And if you look here, which is just a box of random components that I scavenged, you can see these capacitors right here. These are SMD aluminum polymer and SMD tantalum capacitors. These are the same ones as these. If you have empty pads on a card, you could populate them with these if you have some on hand, like you can buy them online or you can just harvest them from other cards like I did. And then there are also multi-layer ceramic capacitors, or MLCCs for short, which are these very, very small ones, which I'm going to also put on the card. Like I'm going to put these on the card, and also these multi-layer ceramics, because we have no SMD aluminum, no SMD polymer spots that are free. They are all populated already. I'm going to add these can-type capacitors to the card and some multi-layer ceramics as well later. So the first rail we're going to be modifying is the VCore rail. So here on the back, the 580 and 480 reference PCB has a very convenient hookup spot for a lot of capacitors, and those are these multi-layer ceramics on the PCB here. It's very convenient to just solder capacitors to those. And you can add a quite significant amount of bulk capacitance to the card this way. So if we take some of these 1000 focus. Yeah, if we take some of these 1000 microfarad capacitors, we can just add them to the card like this, basically. So I've made a dedicated video about cap modding where I said some more things about it if you want to know things. So basically the blue side tells us which side is ground. So with the multimeter you could measure the resistance on each side of the capacitor, and whichever one reads 0 ohms to, well, a common ground, like on the PCI Express connector. So this middle thing is always ground on an NVIDIA card. If it reads 0 ohm, that's the ground side. Here it is kind of easy to see because the SMD polymer capacitors also have an indicator. They have a stripe that indicates the positive side. So you just put the ground side of these to the not positive side. And all the capacitors in this bank are oriented the same way. So it is easy to see which side they have to go. So I would just take some capacitors and, well, solder them on like this. If I can put some more on without, like, basically, yeah. You could add capacitors like that, and then you could add some smaller capacitors to these multi-layer ceramics over here, adding a quite substantial amount of bulk capacitance to the VCore VRM. Now the memory VRM, this capacitor is part of the memory. These two multi-layer ceramics are as well. There isn't that much potential here. You can solder onto these capacitors, these banks of two multi-layer ceramics around the core. These are not on the core rail. These are on the memory rail. This one is as well. So you can solder to those and add some bulk capacitance to the memory, which is also more effective here because it's closer to the actual memory chips. And then in the end, we will add multi-layer ceramics to the memory as well. So you can see each memory chip has two of these slightly larger multi-layer ceramics, and we will add another one of these on top of them or next to them. So we have some more multi-layer ceramics capacitors for the memory as well. If you wonder why we don't just take the biggest capacitor we can find and add it to everything, there's more characteristics to capacitors than just their capacitance. There is equivalent series resistance, equivalent series inductance. Different types of capacitors are good for different kinds of frequencies to filter. That's why you want different kinds of capacitors in your filtering. So that's why we're adding different kinds of capacitors to the card. Now the easiest should be just adding the capacitors to the core VRM, because, well, those are big, those are easy to access, and I guess we just start with that one. So now I have finished attaching the first row of capacitors. As you can see, it is kind of crooked because I was not sure what capacitor, like which of the MLCCs I should use to hook up. So the first two ones are misaligned until I finally decided for the last four ones to always use the more like the top one, looking at like this. Yeah, it doesn't look that great, but they are all attached, which is why you see me like testing this, so that they're not wiggling around, that they really are attached. And now we can add a row of smaller capacitors to these multi-layer ceramics here. It will be kinda hard to get in there on that side, but it should be possible. Yeah, I guess I'm gonna try that now. So, second row of VCore is done. I've added 5 820 microfarad capacitors. Again, you can see in the middle I had an issue with this capacitor because I actually put it on wrong, with the wrong polarity, so it would have blown up the moment I turned the card on, which obviously you don't want. So I removed that, and yeah, and again, because of that, the middle one is kind of crooked, and it doesn't look that great, but I guess it's, I mean, we're extreme overclocking here. We're not making things look better, we're making things go faster. So, yeah, capacitors for VCore are done in that case. I am now going to add, let's get those legs away that I trimmed off. I'm now going to add some capacitors to the memory, specifically these capacitors in the middle. And yeah, that will be the next part. So, bulk capacitance for the memory is now also attached. You see this one is, well, the other way around, because this multi-layer ceramic capacitor here would be obstructed by that bigger capacitor, and I do want to keep this one free to potentially attach multi-layer ceramics next to it or on top of it. So that's why this one is flipped around. The other ones all do not... well, actually, this one obstructs another capacitor, and I didn't notice, so... well... but, yeah. So, memory bulk capacitance is attached now. Now would be the time to take some multi-layer ceramics and attach those also. Those are very small, those are very fiddly. It's, well, a bit annoying to attach those. The good thing about them, though, is they are not polarized, so there's no ground side, there's just, you can orient them whatever you like, so you don't have to measure every time you want to attach one, which makes it a bit easier. So, yeah, time to attach those. And then we will be pretty much finished with our, well, we could attach more behind the core as well. But let's do the memory ones first. So, I have now attached one multi-layer ceramic capacitor to every memory chip. So, you can see them. There's one, there's one, there's one, there's one, and then that goes on for all the memory chips. Ideally, you would want to attach a second one to the other side of the capacitor on every chip, except for this one where I, well, obstructed it. But since I said, like, in the beginning, this memory, which, I mean, since I've taken the card apart, can we see it? We can't really see it, sadly. Well, yeah, like it says Hynix AFR on there. Since this is AFR, and I've worked with it in the past, and it did not scale, neither with voltage nor with capacitors, I'm just gonna, like, it will probably scale a little bit, a very, very tiny amount, but, like, yeah, since I'm not really expecting this to scale really in any meaningful way, I'm not bothering with the second multi-layer ceramic. If you have something that really, really likes capacitance, like a Samsung eDie, then, yeah, it would be very much worth attaching those extra capacitors. But since here it likely won't make a difference, and since this entire mod is more like for demonstration purposes anyway, I, well, just went over those. So pretty much all the capacitors are attached to the card now. There is one more thing you could do. You see at the VRM, there are these empty pads. These are intended for CAN-type capacitors, but with an SMD mount. But these are compatible with SMD, like these capacitors. Like, it's not meant to be compatible, but the pads kinda happen to line up. I don't think, like, I'm not gonna be attaching these because this will need me, like, I will have to use the heat gun or the hot air station. This creates a lot of heat, and it is directly on the other side of these capacitors, and if I heat the board too much, These could actually fall off because the solder becomes soft and well, loose, and then these fall off. So yeah, but you could, well, try to attach those here. It's kind of annoying to do. And you also have to be pretty precise because the base plate, when it goes over here, it blocks a lot of the space around this area. So you couldn't attach like a big CAN-type capacitor like on the back here because the base plate would collide with it. So yeah, this is pretty much the capacitor mod now. And now I would actually reassemble the card and test it. We haven't done the Voltmod yet, but all the capacitors are on the card now. And now we could test what the capacitor mod alone already does for us. And then if we think we need extra voltage, which I'm just gonna do it here. Then yeah, after that we can see what an increase in voltage can do. Okay, I've run the card. I did some benchmarks. I didn't record them because the mod is not finished yet. There's going to be a Voltmod or 2 Voltmods for memory as well. Then, when the card is properly finished, I will show you will show it to you running. I could add some more modular ceramics behind the core. That could also help us a bit, though. Well, I don't know. I could just do it. It's just getting late, and well, I might finish this off tomorrow. So, but talking the impact that only the Capmod had. So, we went from 966 megahertz stable on the core to 985. That's, look here, 985 is pretty much higher than every card except the one Lightning that made it to 1 gigahertz. So that's pretty good already. Then on the memory, we, as expected, scaled a tiny little bit. We scaled 25 megahertz from 2375 to 2400. So, well, this card, the first Lightning, is outclassing us significantly in memory, but we're tying the other 2 G-die cards at 2400 now. So yeah, memory scaled a very little amount, like 25 megahertz. If you're already at 2.5 gigahertz ish in that region, it's not much. On the core, well, that clock is in a much lower range, and yeah, so we didn't scale that like from 66 to 85. But, well, it's still a nice increase, considering we are still on the stock heatsink. And we still haven't changed our average voltage. We have just added more filtering to smooth out the voltage. And only that already scaled, well, made us scale to 985. That's pretty good. So this card could actually do, if I just do the Voltmod and bring it to, say, 1.2 volts, this might actually do 1 gigahertz on the stock heatsink, which not every card can do that. But yeah, so since it's getting late, I think I will finish the rest of this mod tomorrow. But results have been promising so far. And then tomorrow I will add the Voltmod for core, memory, and possibly some more modular ceramics behind the core directly. Then I will show it running, and then I will probably also attach the new water cooling loop to it and run it, well, on water to cool it down even more. We can also delid the core. So yeah, there's still some things we can do to improve the performance of this card. So yeah, but this is as far as I go today. Like the day as I'm recording this, the video will continue after this. So yeah, Only more filtering already brought us some, well, some decent increase on the core. Not much on the memory, but that was to be expected. It is still 1 gigabit AFR. And so yeah, we will continue on then with the Voltmod. So, as you could probably see in the footage, I have not done the Voltmod. I've actually decided to put some more caps on it because, well, I got bored. I actually didn't lie down for the day, so yeah. I've added 8 multi-layer ceramics behind the core, and I added a second capacitor to every chip, including the one where it's obstructed, where I just soldered onto a smaller capacitor, which hopefully works out. So yeah, and I was thinking of maybe putting some other capacitors on the front side that I was showing, but well, I don't think that will be working out that great. So I guess for now this has all the capacitors it can have, so I guess it's time for the Voltmod. So, the Voltmods are now on the card. So the core received a 100 ohm potentiometer and the memory received a 50k potentiometer, so 50,000 ohms. And yeah, that's going to enable all voltage control. So if you... Wait. Camera, why? Why you do this? Well. Seems I can't zoom in right now. Yeah, well, the hookup point, they're not that important. It's meant as an example to see what kind of mods have what impact. That's like, it only applies to the specific card. And if I would do more stuff that applies to only this card, I would also do things to the PEX rail over here, because I've heard lowering this voltage can actually help you increase stability on core, but that's only on this card, not on any other card. I'm demonstrating mods that you can do to every card, like a Capmod. You can most older cards you can BIOS mod, you can Voltmod, and yeah. So now we have voltage control on the core and the memory, and yeah, basically now it's time to put the card in the system and test it out. So the card is now installed in the system. I've already run some tests to not make this video any longer than it has to be. So you can see, card is fully modded in, well, yeah, in the system. I've already set the voltages, so we are at 1.2 volts core under load, like, well, slightly under it. I use GPU-Z render test to make the card go into maximum power state, but actually running a stress test makes the voltage drop a little bit more because of the current draw. But yeah, there we have 1.2 volts, and memory is 1.7 volts. So one interesting bit is that the memory on this card actually seems to like voltage a bit more than my other AFR card that I also modded in this way. So here you can see that's the maximum I could do. So that's 1005 megahertz core, so we did break 1 gigahertz on the stock heatsink, and 2450 memory. Now that's another 50 megahertz higher than just the Capmod on the memory, which that's actually some decent scaling. Like, it's nowhere near as good as EDI. Like EDI, you give it 1.7 volts and you keep it kinda cold. It can actually max the slider at over 2600. But this 2450, that I would actually be okay with. Like 2450, that's decent. That's actually a decent clock. So yeah, this AFR actually didn't stop working at over 1.6 volts, which is interesting. So apparently 1 gigabit Hynix AFR is a memory chip that has a lot of variation in it, because like the other card with 1 gigabit AFR that I had, which was also on the same PCB, that just straight up stopped working. Like, you go anywhere over 1.6 volts, the card just straight up won't boot anymore. And this one just keeps running, and it even goes a bit faster, which is, yeah, that's nice. So AFR isn't that bad. It's still not great. That clock is like, you can reach that on EDI by just having it kinda cold. You can reach it on GDI pretty much stock. But yeah, this clock is okay, I would say. The core, well, we did break 1 gigahertz on the stock heatsink, and so you can see our maximum temperature was 63 degrees, which, if you remember at the beginning of the video in the binning chart, this one actually had 69 degrees at just 1.15 volts, and this is now voltmodded to 1.2, so more voltage means more heat, and it's now running cooler. So when I disassembled the card, you could see for a bit that there was some white thermal paste on there. I don't have any white thermal paste, which means I never repasted the card. This was still on the same thermal paste that the previous owner had, which probably performed very poorly. So that's probably why the temperature is so high now, because that, like 63 at 1.2 volts, like it's on MX4 now. Yeah, that's more like it. But yeah, the card still very much is on the reference heatsink. And the next step would be attaching a water cooler to this and taking it cold. And like, not really cold, like colder than 63 degrees. And yeah, I could actually, well, I could actually go a bit higher on both voltages. It is just, well, memory I would try at almost 1.8 volts, but I usually go just to 1.7. And well, the core, I could go to 1.25, that's kind of the safety limit on the reference PCB. Yeah, I mean, this is already overvolted, and I don't really feel like super pushing it right now. So I think the voltage I've set is already like high enough, I think. Yeah, you could definitely go higher. At some point you also run into the problem that more voltage creates more heat, and it gets so hot that the cooler kinda has to work so hard that you like run hotter, and more heat makes your clock worse. So yeah. I'm pretty satisfied with the results we got here. And yeah, so I'm gonna reseat the camera on something static that I don't have to hold in my hand, and then I'm gonna show it to you running. So here we are, and did you see that black box up there? Yeah, the card crashed when I was testing. Yep, you can see it did crash before, but those are the same settings that just ran. Knowing my luck, this might crash, but it did run those settings. The black boxes are there because I tried more than 2450 memory, which didn't work. So yeah, the card kind of does that, but it shouldn't affect, like, yeah, it not just shouldn't, it doesn't affect the stability right now, except that maybe it crashes now. Actually, I will. Oh, well, time ran out. I wanted to max the fan. Because more cooling, like, it's a Fermi, you want to keep it cold to get high memory clocks. Not memory, I mean core. So here we are. White balance is out of the window again, so you can't see the FPS. We are at around 23, 22, depending on the scene. Now we have 31. Well, the fan kinda went up by itself. So yeah, that's GT1. No artifacts for now. It will probably artifact in GT2 because the memory is really like pushing it. 2450 is pretty much the limit for those memory chips. The core on Fermi usually doesn't artifact, like on 500 series. For 400 series cards artifact actually a lot. When you reach maximum stability on core, on 500 series they just kinda crash. So even 5 MHz more, like this is at 10.5, 10.10 will pretty much crash instantly. And you did see that memory artifact there. It could probably get worse as the memory heats up over the course of the test. Yeah, you can see there's a black thing that shouldn't be there, and it's like flickering. Yeah, the memory is really pushing it. But it did pass in the test run, so there's no reason why it shouldn't pass now. It just kind of looks fun. Well, actually, core artifacting on 480s is much worse than this. So that's the CPU test. I think the CPU may actually be stock. Because I don't remember if I set the BIOS profile. Well, we don't really care about CPU score. We just care about that the card is stable at those clock speeds. So now we get combined. There goes the fan again. And we passed. Oh, wait, what? Wait, why does it say test was can't? What? What are you doing? It passed. Like, you could clearly see that finished. What the? Okay, apparently we like crashed on the very last frame of combined or something. Graphics actually went up a bit. Yeah, the CPU is stock. That's a stock result. Yeah. Artifact. So. Yeah, you can see that this is really pushing it. Oh, we actually went to 6. Yeah, probably because I didn't max the fan. We got a bit hotter, and that probably broke the stability. Actually, that was in GT2. In GT in combined, we actually went up to 63, which was the old limit. Yeah, no idea then. Yeah, I really don't want to rerun it. It's just like, yeah, this is very pushing it. So, yeah, you've seen it running, you've seen that it is very much on the edge. And now we are going to put some proper cooling on the card. So, to get a water cooler on the card, we need to somehow keep our VRM and memory temperatures under control. So I've taken this base plate, which came with another GTX 580 reference PCB. That's now an e-power, but it came with a custom heatsink. It was a MSI Twin Frozer 2 heatsink, and this is the base plate that it comes with. So this is compatible with the reference PCB. And we are going to screw that on to keep our memory and VRM temperatures within check. There is not really a lot of surface area here, but that's still better than nothing. So yeah, because I don't want to run a naked VRM if we have the card in water. Like the core will be very cold, but the rest is probably gonna be very hot. So that's why we put a base plate on it. Okay, so now with the base plate attached, we can do another modification, which is removing the metal IHS. Now, as you can see, this GPU doesn't really look like a GPU because there is a metal piece over the GPU actually. So Fermi cards do have an IHS like CPUs do, and we can remove that. Now, it doesn't work with the stock heatsink if you remove it, which is why I didn't do it before. But if we now use a water block, this will work. And removing the IHS isn't really that complicated. And I have made a video about how to do that. I'm not gonna show it on camera now because it is kind of awkward to film. Like you have to have the card on a like weird angle and you can't really record that. So I'm just gonna do it off camera. If you wanna know how to do it, just look up the video I made. There's also plenty other videos on YouTube. So yeah, I'm going to remove the IHS now. So the Delid is done. And now we have our bare GPU die. As you can see, I removed the base plate again because it was easier to access the die this way. So guess I gotta put it back on now again. And then we can put on our water block. So, the card is on water now. I have already tested new settings. So here it is. Well, it has fans on it to cool the base plate. Radiator is here. This is now a 360 one. This is the new loop. So this is a 360 radiator, the Alpha Cool DDC pump press combo, and the new freeze mod block, which has the tube sticking up and not out the front. And yeah, it also has the very loud OEM fan on it to keep it really cool. So, this is the highest scoring that I got through. So 1035 on the core, 2475 on the memory. If I reset the core to stock, I can actually pass 2500 on memory. Max temperature, as you can see, was 42. I have actually opened the window, so well, we're still at like 41, 40, so it didn't really do a lot. So yeah, clocks have increased a bit on core. That's like 580s don't really like. If you take them really cool, they can gain a lot on core, but like keeping them in the 40-degree range, that's pretty typical of what I see on 580s. And yeah, the memory increased by a lot actually. Like this is now genuinely good memory clocks actually on AFR, which I wasn't expecting. With that said though, I did increase the voltage again, because at the same voltages as before on water, it barely made any difference. The memory just wasn't affected and the core got like 10 megahertz. So I increased VCore to 1.25 and memory to 1.75 volts. So that's where the extra memory clock comes from, because I don't think the temperature did really do anything. And the extra core clock is partly voltage, partly just having the core run colder. And yeah, so that's the kind of score you get. It's the OS is not optimized. I haven't closed things in the background and things, so the score could be better. This should be my score with the direct CO2 on ice water, which was like 19 degrees load. And that card also had the memory slider completely maxed because that card has eDie. Yeah, for just normal water cooling, like ambient, this is pretty much what I like. For core, this is pretty much where I expected to end up. For memory, I am positively surprised. I wasn't expecting this to do so well, partly because I wasn't expecting that there is such a great variance on 1 gigabit AFR memory modules in terms of voltage tolerance. Since again, the other card that I had with the same memory modules literally just stopped working over 1.6 volts, and this one is running 1.75 volts just like a champ. And if you can run more voltage, then, well, guess I found out that memory like AFR has some voltage scaling. Not as good as eDie, but it has voltage scaling. So, yeah. That pretty much ends the video / project. I don't think I can get anything more out of the card now, especially because we are at the safety limit for the VRM. We cannot go higher VCore without risking that the VRM will be overstressed. It is a reference card, and NVIDIA reference cards before the 1080 Ti were always just like, yeah, they're like barely cut it. So 1.25 volts is really the limit here. I'm not going higher. The memory, well, you could maybe try 1.8 volts, but considering that now I can't get both the highest frequencies to pass at the same time, I actually have to reduce memory to get it passed with, like, I can either run high memory, I can run core as high as it goes, but if I can only run high memory if I reset the core to stock. And I, like, at that point, like, getting more memory frequency doesn't really matter because I can't run it anyway. So yeah. That should be pretty much it. So we started at 966, now we are at 1035. That's, I'm bad at math, but a decent increase. Memory, we started at 2375, now we are at 2475, that's another 100 megahertz. It's not much. Like, if it was an eDie card, you would have gotten like 200, maybe even 250 megahertz. But considering I was expecting to gain literally nothing for the memory on this card, this is this is pretty nice. And yeah, so here we have the card completely modded. And so let's go about the do I have it here? Yes, I have it on a list. So, stock, I just said, we had 966 core, we had 2375 MEM. Then, with only the Capmod, the first, like, I mean, I added some more multi-layer ceramics after. The Capmod, we had 985 core and 2400 memory. Then, with the Voltmods active, we had 1005 core and 2450 MEM. And now on water cooling and with upping the voltage again a little bit, we have 1035 core and 2500 MEM maximum, but only usable up to 2475 if you run the core high as well. And sorry, the air is really dry in here. It's not the beer virus, trust me. Considering that on 580s, most of your GPU score comes from the core. Yeah, so the core is more important for score than the memory. So when I was testing the core, I was running the memory stock. I got like 6000 GPU score. So that's about what your memory overclock gives you. It's not much. So, yeah. And I guess we're finished now. So, yeah, that's pretty much what you can, well, that's the full rundown of fully modding a graphics card. Benching it, just like trying to get, like, I didn't go super extreme, like I could run ice water, I could, like, if I had liquid nitrogen I could do that. Then I would like to e-power the card, because at that point the VRM won't hold, but like reasonable extreme overclocking. This is as far as I would go. And yeah, so I hope this kinda, well, I mean, the point of this video was to show what kind of mods you do and what kind of impact they have, which is why I gave all the maximum clock speeds for all the different stages, so you can kind of see what does what. So yeah, thank you all for watching, hope you enjoyed, and until next time, goodbye.